All right, we're going to continue with the answers for the day 35-36 video. So the next question up is, what is the formula for RMS speed of a gas molecule? So the answer to that is U equals 3RT over molar mass. It's in your book. It's also in the video, the instruction video. So you should watch the instruction video before you're doing this. You don't have to answer any questions there. It's just to give you the primary information for this. Okay. Of the four gas variables, N, P, V, and T, which have an effect on the speed of the gas? Okay. The answer to that is only T. Okay, so only T affects the speed of the gas. Temperature is the average kinetic energy of particles. So temperature means, when temperature goes up, it means the kinetic energy has gone up. If you look over on this side of the equation, the mass of the particle, the gas particle, can't change. The only thing that can change if Ke goes up is V. That's the speed of the particle. If T goes down, Ke goes down. Again, the only thing on this side that can change is the velocity. That means the velocity must go down. So the only thing that that changes can have an effect on the speed of the particle is the temperature. Okay, I want to go back to 15. I want to add something about this that's very, very important. Otherwise, you will not get a correct answer. And that is the value of R. There is a different value of R. I'm not going to show you how you get to the one that we are used to. This is the one we're used to. There's a different one, however, and it can be derived from this one. It would take a lot of math and a lot of other units of measure that we don't use in this class to do it. So I'm not going to do that. It's too much information. So I'm going to go ahead and just write it down here. And it is this. It's hardly ever used. This one is used almost all the time because this one's the one used with PV equals nRT. But the other one is this. The J is joules, which is the unit of measure of energy. This is the one that we use in this equation. Okay, so you just have to remember the number. And again, normally I ask you to, understand the unit of measure cancellation. You will not unless I write this in a different way. So I'm simply going to say that the unit of measure for your final answer here, it's speed, and it's going to be the unit that you used in physics class most of the time, which is meters per second. Okay, this is the one time I'm going to ask you to just kind of accept this on faith. They would never ask you to derive this or explain it on the AP exam. It's like too much information. It's off topic. But you should understand you need to use this one here, and you're going to come out with meters per second as the unit of measure for this equation. So it's a speed. It's a velocity, okay? Really a speed. Okay, so here we go. Let's come on down here now. What is the RMS speed of helium gas at 25 degrees centigrade? So you need to have temperature. I see that there is a blue tint to this screen. I don't know what's causing that, and I hope to get it resolved. But for right now, we're going to have to live with it. I don't think it obscures your vision. It's just a little annoying because it kind of moves around a little bit, okay? That's 298 Kelvin. Molar mass for helium, that's easy. That's 4. You get that straight off the periodic table. Okay. And technically it's grams for molar mass. It's grams per mole. Okay. But we're not going to worry, since I'm not going to have you cancel the units of measure for the reason I just explained. I'm not going to worry too much about that. What else do we have? We have R. It's the new value of R we're going to be using. And that's it. So we're going to go ahead and plug in. So U, in this case, is going to equal okay, we are going to crunch the numbers here. So I'm going to take the square root of 3 times 8.314 times 298 and divide that by 4. And that gets us 43.1. We have, well, this is actually 4.00. We can go to 3 significant figures, 43.1 meters per second. Again, it's math-magic here, that how you get from these units to meters per second, simply because I'm not going to show you the derivation. It's just not worth the time. Just to understand that, and you do enough problems of these types, so it's meters per second, that will come through. So I'm going to ask you to do this one down here for O2, right there. So O2 is molar mass. You can look that up on the periodic table. Remember, there's 2 oxygen that you're dealing with. There's your temperature, and go ahead and do the same calculation there. Okay, 19. Consider a mixture of gas A and B in a closed vessel. The quantity of a third gas C is added to the same vessel at the same temperature. How does the addition of C affect the following? The partial pressure of A. Okay? So the answer is it doesn't affect the partial pressure of A. The partial pressure of A is what it is, whether there's other gases in there or not. Their pressures are independent of each other. So it's good to write all that out to be sure you're clear on the concept. Partial pressure of A, partial pressure of C. The total pressure in the vessel, it's going to increase it. You keep adding pressures, they just add linearly. So okay, so just straight up adding something, it's going to make it go up. The mole fraction of B, okay, that's going to cause that to go down. So let's just express that as a before and after. Before and let's use the proper expression. So it's that X, it's a chi, but I'll write it out since it's new to you. Okay, so before what you had was this for mole fraction. Of B would be number of moles of B over number of moles of A plus number of moles of B. After your mole fraction, and I should put a B here, subscripts, get on the screen. After mole fraction of B number of moles of B over number of moles of A plus number of moles of B plus number of moles of C. So you've increased the denominator down here. So the mole fraction, I'll write it in between. The mole fraction of B decreases because that denominator increased when you added C. So it's a smaller fraction than that would be. Okay, let's go ahead and move on. We're going to do this problem right here. It's got a lot of numbers in it, and in fact, you'll notice it comes from your textbook. That's just my way of referencing the textbook. It's Brown, LeMay, Burston. And it comes from chapter 10, and it's question number 67. So it's pretty far into the textbook. You know, not quite halfway, but almost. And it's problem 67 in that chapter. So this is not a trivial problem. So let's go ahead and sort out all these numbers. So you have a sample of 3 grams of SO2 gas is transferred to a 10-liter vessel at 26 degrees centigrade. A sample of 2.35 grams of N2 is transferred to the same 10-liter vessel. What is the partial pressure of the SO2 gas in the larger container? Okay, well, the moment you saw grams here, you probably, if you're thinking, you probably said, okay, we're going to have to convert that to moles. We don't do anything in chemistry in grams other than weigh things in the lab, and then we have to convert to moles to actually do chemistry. Okay, so let's go ahead and let's put this over here. Let's figure out the molar masses of these two. So you have 3.00 grams of SO2. I'm not going to write the SO2 there because I already wrote it there. Times, and you have to come over here. So it's O2 is going to be 32, of course, and S is going to add another 32. So that's 64.07. And that is going to give you 0.046, and that is moles of SO2. Okay, same with nitrogen. It says that we have 2.35 grams of N2. And again, we come over here. Nitrogen is 14.01. There's 2 atoms per molecule, so it's 2 times 14.01. And that gives 0.84. I keep forgetting to say 0.84. There you go. And that's moles of N2. Okay, good. So now we have, for each gas, we have moles, we have volume, we have temperature. We're going to have to convert temperature. So let's do that up here. They're both at the same temperature. When you put something in a container, it doesn't matter what temperature they were at, they're going to end up being at the same temperature. So temperature equals 26. And that's going to bring us to 299 K. Okay, so temperature's there, volume's there, number of moles, and what we're trying to figure out is pressure. So if we have PV equals nRT, divide both sides by volume, and you end up with P equals nRT over V. Okay, so now what we can do is we can plug in for each of these the number of moles. The temperature is going to be the same, volume is the same. So the number of moles over here of SO2, same thing, number of moles of N2, and that'll give us the partial pressure of each of those. Now they're asking for the partial pressure of N2, so let's go ahead and do that one. So the pressure, the way you designate that is you use the pressure and then N2 subscript equals the number of moles is this. Okay, and that's moles. Okay, just to conserve space, I'm not going to write the units here, just to save space, okay? But they will cancel to give you pressure in atmospheres, okay? Because that's what R is calibrated in. So I'm just going to cheat a little and not write the units here. It's 0.821. Okay, and times the temperature we got up here is 299. And that's all going to be over the volume, and that's going to be 10 liters. Okay, so that gives us the partial pressure of N2 It's just simply all of that, and it's going to come out in atmospheres because that's what R is calibrated in. So 0.084. And that gives us a pressure of 0.206. I can see I'm limited to 3 sig figs, so I'm going to put that there. All right. Now they want to know the total pressure. Well, in order to get the total pressure, you're going to have to figure out the pressure of the SO2. There's no other way to get there. So let's go ahead and do that. Same thing down here for SO2. This time we're using 0.046. And again, I'll skip the units of measure. And same volume, same temperature. So you go ahead and you want to do that, SO2. Okay, and that gives us 0.113 atmospheres. Okay, so this is partial pressure of SO2, partial pressure of nitrogen. So the formula for total pressure is P total. Okay, and that gives us 0.319 atmospheres for our final answer for this total pressure in the vessel. Okay, so if you got that, if you understand that, good job. You're, well into the textbook right here. That's kind of a good feeling. Okay, let's do a combined gas law. And again, it's just a lot of numbers. You got 6 variables. These are really not that hard. They're going to give you 5 of them, and you got to figure out the 6th one. So that's all it is. So a 9-liter gas container holds O2 gas at 734 torr and 28 degrees C. Now notice something about this question. There's no gas constant here which has the units of measure already set up. You don't have liter atmosphere over mole Kelvin. So you can go ahead and work this problem in torr. That's perfectly acceptable. Okay? Because the bottom line is they're going to ask, the temperature is increased to 38 degrees C, what is the new pressure? So you can express the pressure in torr. That's no problem with that. With the gas constant R, where you have fixed units of measure, you have to have it in atmospheres, but not for this one. So let's go ahead and just plug the numbers in and then just do the algebra. So it's a 9-liter gas container. So over here we're going to have what this means, P1, V1, T1. It means the pressure before you've made a change, and then what's the new pressure, volume, temperature after you've made the change. So over here on the right, the volume is 9 liters. And on the left, it's glass container. So it's a fixed volume container. It's not a balloon. So it's also going to be 9 liters. So we've taken care of volume. All right, the temperature is 28 C, and it is increased to 38 C. So again, you have to do 28 plus 273. And that's going to bring you to 301 Kelvin. And the temperature is increased to 38. And that's going to be 313 Kelvin. So that's the after temperature. This is the T2, and this one's the T1. That's before the change. Okay, so we'll come over here. We've got 301 down here. And sorry, messed up. 311. 10 degrees more, right? 10 degrees, 10 degrees. A degree on each of the scales is exactly the same. The only difference is what they call 0. So 10 degree difference, 10 degree difference. Okay, let's go back here then. 311 Kelvin. Okay, and then it wants to know the new pressure. That's the pressure after, so that's P2. And the pressure before is 734 torr. So you can see these are really not hard. Just a lot of numbers and a lot of arithmetic. Okay, so if we solve for P2, it means we're going to divide by this and multiply both sides by this. So let's go ahead and do that. So I just copied these two. Now I got to multiply top and bottom of both sides by this, so this is going to cancel out. It's going to end up there. And then down on the bottom we have 301K here. Okay, and then we got to divide both sides by this, so this one cancels on this side. You're left with only P2, so that puts the 9 liters there. And you notice that's going to cancel out because the volume didn't change, and that's going to give us P2. Okay, so 9 liters and 9 liters cancels out. Kelvin and Kelvin is going to cancel out when you divide these numbers, and all you have left is torr, which is what your final unit of measure is. So let's go ahead and do that, and it gives us 758 torr. So P2 is 758, and I'm looking around for significant figures, and you know, there's 3, there's 2 there, so we probably should just go with 2. So it should be technically 760, but I'm going to leave it like this. Okay, 7.6. So what happened? Let's think about what happened. The temperature increased. We've talked about this before. When temperature goes up, the molecules move faster. They hit the sides of the container more often, therefore pressure goes up. So when the temperature went up from 301 to 311, 28 to 38 sounds like a big jump. It sounds like 1/3 again as much. But this, 301 to 311, that doesn't sound like quite as big a jump. You're always interested in the, you know, how much relative to these numbers did it go up? It just only went up 10 degrees relative to 300. That's not really all that much. So the pressure therefore went from 734 up to 758. Okay, so the molecules are moving faster. They're hitting the sides more often and creating higher pressure. Okay, so this video's reached about 30 minutes. I have a few more problems to do on this assignment. I'll go ahead and do those on another video. I'll get this one posted for you. And so we'll see you on the next video.